Okay, so now let us look at the Ricart Agrawala algorithm for mutual exclusion. Look, the description is given here, but we will look at through an example. The idea behind actually Ricart Agrawala is it combines the reply and release messages of Lambert's algorithm. Remember, in Lambert's algorithm, what we do is each process requesting a CS access will broadcast a request message and, of course, put the request in the queue, and then every other process will send a reply message and then basically put that request in the queue in the increasing order of timestamps. And then the particular process whose request is in the front of the queue and has got the reply from all the messages will then go ahead and execute the CS, and then we'll send a release message to the other processes after finishing the CS execution. So what Ricart Agrawala does is, if you think the other process's request has a larger timestamp than your own CS request, then don't send a reply message and send the defer the reply basically, and send the reply message only after completing the CS execution. So that's actually a kind of optimization that Lamport suggested, but he suggested send the release message. But what Ricart Agrawala said is we can send it as a reply message, and also Ricart Agrawala got rid of the queues at the processes, as we'll see now. Okay, so the way Ricart Agrawala algorithm works is, again, the process wishing to access the CS sends out the request message, and of course the request message is timestamped, so here I explicitly put the timestamp of the request message. Even in Lamports you have to send your timestamp, because that's how the other processes get to know the timestamp of your request message and queue it in the process queue. Now the idea is, especially look at this process P2, it doesn't have any CS execution request on its own, so there's no need for P2 to queue all those request messages. So if a process like P2 does not have any CS execution request, it can send simply a reply to whoever is requesting. Okay, so P2 sends a reply to P3 as well as to P1, and the reply message is to be considered as a kind of an authorization by this process to the other process to go ahead and do whatever it wants in the CS. As far as P2 is concerned, in this case, it's not concerned about P1 or P3 entering the CS. So it has given them the permission, because P2 by itself is not executing, or is not wishing to execute any critical section. Now look at P1 and P3. Both of them want to execute a critical section, but P3's request is having lower timestamp than P1's request. So what P1 has to do is, it has to kind of let P3 to go ahead and execute the critical section request, because P1 knows its request is having a larger timestamp. So at least now when you look at P1, it knows that some other process is having a larger timestamp, so it goes ahead and lets the process to do whatever it wants with the critical section, since it's the authorization. So P3 is going to be the only process in this case that would have got all the reply messages from the other processes. Okay, but P3 is not going to send a reply message to P1, because P3 knows its own request is having a lower timestamp than P1's request. So P3 is going to buffer the request of P1 in its queue. So that's the only time you need to buffer the CS access request, that when you have your own request having a lower timestamp, you have deferred the reply to the other process, so you have to buffer those requests in your queue. So now the process P3 can actually go to the CS and execute the critical request section, because it has got the reply messages from the other processes. So when you get the reply message from other processes, it means they've authorized you to go to the critical section as far as they are concerned. So the process P3 can go to the critical section and execute it, and when it comes out, it sends a reply message to all the deferred requests. So in this example, we have only P1's request being deferred, but if we have deferred the critical section access to more than one process, just go ahead and send a reply to every process, because you cannot execute more than one critical section at a time, or same critical section more than once, because the other processes are waiting to execute the critical section. So which means even if you have multiple critical sections to execute, you have to, if some other process is waiting, you have to again come out and send out the request messages. But in this case, P1 is the only process waiting, so just send a reply to that process. Now, when you send a reply to P1, what P3 basically indicates is it is giving P1 the authorization to go ahead and execute the critical section. And P3 by itself doesn't have any more further request to access the critical section, right? Okay, so when P1 gets the reply message from P3, it has already got the reply from P2, so both the processes have authorized P1 now to go ahead and execute the critical section. So P1 goes and executes the critical section. Now, what optimization that Ricart Agrawala, or actually the other people here, these two people, proposed is, another level of optimization is this. The like this P1, it has got the reply message from P3 and has already got the reply from P2. And as I said, when a process sends you a reply, it means it has authorized you to go ahead and execute the critical section. And after P1 is done with its execution of the CS for the first time, when it comes out of it and it sees that nobody else has sent a request message to critical section, and if P1 again wants to go ahead and execute the critical section, it can go. It need not go through a request reply process, because if the other processes want to execute the critical section, they would have sent a request message now, and they have not sent anything. So you can consider the reply itself as a kind of implicit approval for these processes to let P1 to access the critical section again. So you can repeatedly go to the critical section and execute it until some other process sends you the request message. And this will provide you still all the fairness, safety, and liveness, because to execute the critical section, you need the reply message from every other process. And in terms of liveness, once you have made the request, all the processes are going to consider your request in the increasing order of timestamps. So if, as I said, if P3 comes out of the critical section and it sees P1's request in the queue, if even P3 now makes its own request, its request will be queued behind P1's request. So P3 is going to release the critical section and send a reply message to P1 and let P1 to execute it. But if P3 had a request, it would have also sent a request following the reply message, and the channels forward messages in a FIFO manner. So a process's request to access critical section will be eventually granted permission. So there's liveness as well as fairness. So as I said, if a process exiting out of the CS has to again go back to the CS and there's a waiting critical section request, then that waiting request is given all the priority, and that process can enter the critical section like P1 did in this case. So there's fairness in the sense that the critical sections are executed in the order in which the requests are generated. Now, in terms of the complexity, the message complexities, to access the critical section, you have to basically send out the request message to every other process and wait for the reply message from all the other processes. So it is n-1 request and n-1 reply, so it is 2 times n-1 number of messages. And after this particular process is done with this critical section execution, it sends out a reply message to all the deferred requests. So it's basically a kind of broadcast sent out to all the deferred processes whose request has been deferred. So it is one propagation delay of the reply messages. And so system throughput is 1 over t plus e. Now if you incorporate this optimization, like in this case, P1 doesn't need to send out any request or doesn't need to wait for any reply. So the number of messages you need for CS invocation could be even 0. But at the worst case, you would have to broadcast to all the processes and the request message to all the other processes, so n-1 requests, and then wait for n-1 replies. But they could be even in between. So for P2 may not have any CS access requests, So you don't need to send actually a request message to P2 because P2 has not the reply message that you got from P2 itself is an indication that it's kind of authorizing P1. So until you get say a request message from P3, P1 can repeatedly go to the critical section, P2 or P3. So until some other process sends a request message, you can keep on going to the critical section. And when you get a request message, you have to release a critical section after done with the current execution and send a reply message, and then wait for a reply message from the other process. So you see that. So the number of messages you need for invoking the critical section could be anywhere now between 0 to 2 times n minus 1. Okay. So now in terms of this, the complexity becomes big O of n because it could be at most 2 times n minus 1. Okay. So we discussed about all the three properties: safety, liveness, and fairness.